Hi, good morning. So today we're looking at section 10.2, which is about infinite series. The rest of this unit is based off of infinite series. It's one of those ideas that you really want to have a good grasp of it now before you go any further. So here's the big question. Is it possible for a sum of an infinite collection of non-zero numbers to be finite? Well, I'll break this down a little bit. Sum, so we're adding things together. Infinite collection, so we're adding numbers that are not zero to be finite. Do you have a value? So it feels like if you have some numbers and you keep adding more numbers, that sum would get larger and larger and larger and go all the way to infinity. The truth is that's not the case. And this example that's in front of us is really the best way to visualize that. If we have a box that's 1 unit by 1 unit, right, 1 by 1, the area would be 1. 1 times 1 is 1. Now, if I take that and cut it in half, all right, there's a piece that's 1/2. Great. If I take the next piece and cut it in half, I have 1/4 plus the next piece in 1/2 is 1/8 and 1/16 and 1/32 all the way through. So this pattern could keep going on forever and ever and ever and ever. There would be no end to it. It could keep going. But if I add the sums and I think of these as all areas, if I continue to add those together, what would the total sum be? Well, the total sum would be 1 because that was the area of the box to begin with. So even though we have an infinite number of terms that are being added together, the sum would still be 1. And this word series applies to that sequence that we had yesterday when we add them together. When we have the sum of a sequence, that's the series. So you're going to add and subtract those together. Now, if you're more into numbers than pictures, let's look at a partial sum. And this is where we look for a trend to determine an infinite sum. So if I just have that one term, I have 1/2. 2 terms gives me sum of 0.75. 3 terms gives me 0.08. 4 terms gives me 0.93. 5 terms gives me 0.96. If we kept adding terms on there, what do you suppose we would get closer to? This reminds me very much of limits, that first unit we had together, but this total is getting closer and closer and closer to 1. This is an example of an infinite series. Or simply, we just call it a series. You don't need the word infinite in there. So what's our formal definition of an infinite series? If a sub 1, a sub 2, a sub n is an infinite collection of numbers, the expression k equals 1 to infinity, sigma a to k of all these terms is called an infinite series or a series. So for example 1, we want to find the sequence of partial sums of this series. So I've written out the series notation. Here's my expanded form, but let's go through and evaluate this. So I have 1/2 plus 1/4 plus 1/8 plus 1/16 dot, 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 dot. We want to know what this is increasing to. So this is kind of similar. No, not similar. This is the exact one that we have above. So we're not going to spend too much time on this, but let me write it out and you can do the same. So what I've done is I've written out the partial sums like we had higher up in our notes.
So what?
I have the totals 1/2, 3/4, and 7/8. Now, you can go through all the work of expanding this out and figuring out what the pattern is, but I'm just going to jump right to it. 1 minus 1/2, 1 minus 1/4, and 1 minus 1/8. These are all the same things as 1/2, 3/4, and 7/8. And that pattern would continue the higher up I go. In fact, the sum of any number of terms is given by 1 minus 1/2 to the n power. And if you look at this formula here, it actually holds out for all 3 of these. So the question then is, what is the limit as n approaches infinity, going back to limits, of an n number of terms? So if we have an infinite number of terms, 1 minus 2 to the n, 1 minus 2 to the infinity is infinity, 1/infinity is 0, and the answer is 1. All right, convergence and divergence of an infinite series. This is what we're looking at for the majority of the rest of the unit. does a series converge or does a series diverge? And so what do I mean by that? If the sequence of partial sums of an infinite series has a limit s, then the series converges. It is said to have a sum of s. That is, the limit as n approaches infinity of s sub n is equal to s. We know that we have an answer. There's a value there. If that limit goes to infinity, we say that this series diverges. So if the limit does not exist, we say that the series diverges. So if you come up with an answer, and it doesn't matter what that answer is, if you come up with an exact sum, we use the word converges. If you get infinity or does not exist, we say that it diverges. So example 2, we want to show that this entire series is equal to 1, no matter how high we go. This one is a very specific example. This is called a telescoping sum. So for example 2, we're looking at this particular sequence. This will wind up to be called a telescoping sum. Now, I left this part over here blank. I want to fill this in so that we know what this looks like. I would have 1/2 plus 1/6 plus 1/12. And the next one would be 4 times 5 on the bottom would be 1/20, ... We want to know that this sum is equal to 1. So how do we do this? We're going to start with some partial sums. We're going to look for a pattern. So if I have the sum of one term, I know that that is 1/1 times 2. If I have 2 terms, it's 1/1 times 2 plus 1/2 times 3. If I have 3 terms, it's 1/1 times 2 plus 1/2 times 3 plus 1/3 times 4. And 4 terms. Same idea. Okay, looks something like that. Now, if you keep going, but you can see a pattern. This would be 1/n times the quantity n plus 1, because the second piece is always 1 larger than the number of terms that we have. So this is what those partial sums would look like. Now, if I look at 1/n times n plus 1, if I use partial fraction decomposition, you can take my word on this, or you can work on the side and break that apart. That's with the A and the B on the top. I know that this is equal to 1/n minus 1/. You can take my word on the partial fraction decomposition and know that this is 1/n minus 1/n plus 1, which is really kind of handy. So if I look at these, instead of using the sum written out the way that it is on the left, I can now write it out on the right. So this would be 1/1 minus 1/2. This would be 1/1 minus 1/2 plus 1/2 minus 1/3. The next one is 1/1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. Now I'm totally out of space and I probably lost you a little bit here. But the idea is this. Here's a -1/2 and a +1/2. Those will cancel. I have a -1/2 and a +1/2. Those will cancel. A -1/3 and a +1/3. Those will cancel. So all the interior terms cancel, and you are left with the initial one, this 1/1, and this 1/n plus 1. So the sum, the partial sum is 1/1 minus n plus 1. That's what it will always turn out to be. Now, if we want to look at this, the limit as n approaches infinity of 1 minus 1 over n plus 1, 1 minus 1 over infinity, 1 minus 0. Result is 1. So I apologize that this went off the page a little bit, but that's the way that it works. Example 3, show that this sequence diverges. We're going to investigate this one using partial sums as well. So if I look at one term, I know that it's -1. If I look at two terms, it's -1 plus 1, so that's 0. If I look at three terms, it's -1 plus 1 minus 1, this is -1. If I look at four terms, it's -1 plus 1 minus 1 plus 1, which is equal to 0 again. So I think you can see that this is going to alternate between +1 and not -1. I think you can see that this will alternate between -1 and 0. Because of that, it does not approach any one value. There is no limit. So we would say that the limit as n approaches infinity of s sub n, it doesn't go to infinity, but it does not exist. So therefore, we can say that the sequence diverges. Actually, we can say the series diverges. We didn't approach some value, we didn't approach 1, so we say the series diverges. Example 4, determine whether the following series converges or diverges. This one's probably pretty easy. Again, if you look at partial sums, the first term is 1. I add the first two terms, I have 1 plus 2, which is 3. If I add the first three terms, it's 1 plus 2 plus 3, which is 6. The first four terms is 1 plus 2 plus 3 plus 4. So that is equal to 10. So I know that that's getting larger and larger and larger. The limit as n approaches infinity as f sub n of s sub n is equal to infinity. So we say the series diverges. So again, the idea of infinity is now divergence. A geometric series, these are pretty good. A series of the specific form a times r to the k is called a geometric series with ratio r. So what you're looking for is you're looking for some quantity raised to an exponent. This becomes your r. That's a big deal. It can be multiplied by anything in the front, but this is your geometric series. We're going to be on the lookout for those. Geometric series are unique in that we can always find the sum. Some of the other ones that we'll do later, you can't find the sum. We know that there is a sum, but we can't actually calculate it. For a geometric series, you can actually calculate it. So if r is equal to 1, less than 1, we say that the series converges and the sum is given by this formula. If r is greater than or equal to 1, we say that the series diverges. So here's what you're going to do for example 5. You're going to take these 6 problems. R is your 2/5. A is the 8 in the front. And then we are going to calculate which each one of these is. All right, so for example 5, what I have done is taken each of these geometric series and I have written out the work as to how you would find this sum. So as a reminder, that's a sum for all of the terms in that series. So it's an infinite number of terms that are being added together. And you can actually find that sum. So the work's already written out, but let me talk them through them with you. For letter A, over here, we have a over 1 minus r. This one's pretty straightforward. A is that coefficient in the front, which is 8. R is the 2/5, so subtract some fractions, multiply by the reciprocal, and we wind up with 40 over 3. For letter B, everything's in the correct form. I have an a of 1 in the front. We don't see it, so we use an a value of 1. that fraction or that ratio is -5/9. Do include the negative when you go to use the sum formula. And then a little bit of fraction addition, multiplied by the reciprocal, 9/14. Letter C tricked me. The first time I did it, I went to put all the pieces together and I think I got a 6. I went to check my answer and it said diverges. What the heck? 3/2. Because that ratio is greater than or equal to 1, this diverges. There is no sum to find. It would keep going to infinity and get larger and larger and larger and larger, which makes sense. So diverges. Letter D is all the way over here. Now, this one's a little bit tricky. Let me zoom in here and tell you what I did. It's not in the correct form. It doesn't have that r to the k minus 1. So what you're going to do is rewrite this fraction to the k power. The whole thing's to the k power. How are you allowed to do that? The 1 is really helpful in that 1 to any exponent is still 1. So you can put a k on here. So what's not written where this arrow is 1 to the k over 2 to the k. And then because they're both to the same exponent, it's 1/2 to the k. So that gets your exponent to the top. And then how do you turn it into a k minus 1? Well, you pull 1 off of it. So if I had, for example, let's come over here. If I had x cubed, let's go higher, x to the 34th. I could rewrite that as x times x to the 32nd. I would take 1 off of that exponent. So that's exactly what's happening here. You're taking the 1/2 to the front, and that's to the first power, and then you have 1/2 to the k minus 1. So now when I look at letter D, I can go into the formula. 1/2 is the a value, which I'm just putting in the front instead of in the numerator. Same thing. And then I've got 1/1 minus 1/2. Divide all that out, and I wind up with a 1. Letter E, straightforward, ready to go? No, it's not. What's wrong with letter E? Letter E starts at 0. So you have an extra term in there of 1/3. All right, so I have half of it, but I don't have the whole thing. What I didn't take into account for letter E was this. If I have this series that starts at 0, in order for it to start at 1, you would have to take one of these in the front. So I have a 1/3. This is kind of like my k to the 0 term, k equals 0. So this is to the -1 plus the summation k equals 1 to infinity of 1/3 to the k minus 1. Okay. So now when I do that, this first piece, this 1/3 to the -1 becomes a 3. And for the second piece over here, that's all correct. And this is everything that I have written here. So this is actually going to be 3 plus 3/2, which would be 6, 9/2. Yes, this is 9/2. So this is the correct answer for letter E. Okay, good. And then letter F. Letter F is another kind of funky one going on here. Probably one of the toughest things about these series is remembering all the exponent rules from pre-algebra and algebra 1. We use the basic ones, but now we're looking at them through a slightly different lens. And those specific cases now become the normal. So those specific special cases, the negative exponents, the zeros, those are the things we really need to focus on here. So with letter F, what I did was I took the 10 and the 9, and I broke it apart into 2 separate bases. I've got 10 to the k and 10 to the 1, and 9 to the k and 9 to the -2. Your textbook does something similar. They just rewrote it in a slightly different order. I'm definitely looking at this more like an algebra teacher, and how would we break this apart if we were in an algebra class? Then I know that
10 and 9 are both to the k power, so I group those together. 10 to the first is right here. 9 to the -2, I can bring to the numerator. And we have that going on. Now, this is to the k power. I need that k minus 1. So the same thing, I'm going to break that apart. I'm going to have a 10/9 to the first and a 10/9 to the k minus 1. And so that's what's happening here. I've broken those apart. And so if I clean all this up, I'm going to cancel out a 9, cancel out a 9, multiply the two 10s. So 9 times 100, 10 over 9 to the k minus 1. Now it's in the correct form for that geometric series. But after all of that work, what's your R? The first question should always be, what's R? R is 10 over 9. But because 10 over 9 is greater than 1, this whole thing diverges. So they're really not bad. They just take a little bit of practice. And then I have for you the harmonic series. We're going to talk about this one lots and lots and lots, and we're going to use it with something called the p-test later on, which you'll probably remember more of. We could use it with something called the integral test later on, but just know that the harmonic series diverges. So this one feels like it should converge. It feels like we're adding fractions, small fractions, right? 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. The problem is the fractions don't get small enough fast enough to come up with a definite sum. So therefore, the harmonic series diverges. But we'll have some other ways to prove that that's true other than me just putting it in a yellow box. So give these a try. It would be to your benefit to try the assignment before we get to 10.3. You really don't want to let these build up, because I'm just going to have, here's a rule, here's the test, converge or diverge. Here's the test, converge or diverge. So you really, really, really want to get these mastered as we go through them. All right, good luck. Let me know what questions you have.